Then welcome to the 6th lecture in the Lattice Boltzmann methods, asymptotic analysis in moment form. So this is a very central lecture of this series, not only because it is the middle of the semester, but it's also a very important content of how we understand what we are doing. Okay, I've written a few things down, and probably you are not able to write everything down. It's also probably not very important. It will be in the notes, of course, but I wanted to give this small overview. If you want to edit later, you can leave half page empty or so. So the technique we are going to learn is can be used to first of all determine convergence orders, but this is relatively simple. We can actually derive the partial differential equations of a method that we are solving, and we can get exact expressions which are also partial differential equations of the error terms. Yeah, so exact algebraic expressions. This method is, even though it can be used to derive new methods, is actually there to analyze existing methods, and is also, invented much later than Lattice Boltzmann. So Lattice Boltzmann comes from physicists. They think something up, and then mathematicians were horrified. So what is this thing solving? Yeah. This technique is, there are other analysis methods like von Neumann analysis, that are numeric. This is an algebraic method, so it can be used also with unknown parameters, and in order to get these parameters out of the equation. Other than, for example, the Neumann analysis, it does not require any linearization. It's applicable to nonlinear problems. And as I said, it's not data-based, it's just analytic, so it requires no simulation. And of course, you can apply this also to other things than Lattice Boltzmann. Okay, that's what I just wanted to say. And then comes the challenge of today is to derive the partial differential equations that are solved by the D2Q9 LBGK method. And the LBGK methods, or the method associated with this particular lattice. So this is the lattice, and I remind you of our nomenclature with the Miller indices. Yeah, we have here the population F01. Here we have 0, -1. Here we have 1, 0. Here we have F -1, 0. And then we have here 1, 1, -1, -1. We have here 1, -1. And here F -1, 1. I hope I did not mess this up. Yeah, so this is our lattice. So we have the populations Fij, where I and j are the elements of 1, 0, -1, 0, and +1. Okay, so I guess most of you will know this. Let's come to the Lattice Boltzmann equation, the thing we are solving with the Lattice Boltzmann methods. So writing down the Lattice Boltzmann method in equation form. So, and this is, we need to keep track of our equations today, so this will be equation number 6.0. And I write the Lattice Boltzmann equation in a little bit a modernized form. I have the pre-collision distribution Fij at a position x and to this position x I add a movement delta x half, so I move from the position x 1/2 grid spacing in the direction of where the population is flying. Yeah? And I look at this at time step t, which is the collision time, plus half a time step. So what I'm doing is I'm not looking at the collision time, but I'm looking in the middle of the streaming time. Yeah? So where the particle or the population is in between two nodes and when we're in between two time steps. Okay? So basically, you could always say this is something that does not necessarily exist in the method, if you will. Yeah? But never mind. So from this, so this would be equal, the pre-collision state is equal to a post-collision state from the previous time step, obviously, yeah, but I want to be everything on the same side, so I take here minus f post-collision ij, and now this is the previous time step, and because we went half time step, it will now be half time step back, it will be, okay, I go full time step back, but because I have already a half grid spacing, I have to go half, I will end up at half grid spacing again, and I will also end up at half a time step before the last collision. So this thing is basically the Lattice Boltzmann equation, and of course these here are unit vectors in the direction of x and y, so they have magnitude 1. Okay, the BGK, this Lattice Boltzmann equation does not indicate how the collision is actually performed. Yeah, so there are different ways of performing the collision, and today we'll challenge us only with the very basic form of the BGK equation, collision. So this gives us, it will be 6.2 Fij, so at a time step, so this is at a grid node and at a time step, so x and t, not moved. The collision is the difference between the pre-collision, or it's the post-collision minus the pre-collision. This is what the collision, and this is equal to omega Fij equilibrium minus Fij, and as we learned, this omega is not equal to 1 over tau, but due to the implicit nature, this can be rewritten to be implicit. Okay, so what we are doing in numerics to analyze methods is usually always starting from the Taylor expansion. We use a Taylor expansion, and the thing that we can expand is, of course, the equation 6.1. And we expand this at the grid position x and the time t. Yeah? So we see there are offsets, and we can expand them. Okay, I hope, even though this looks a little bit ugly, because now we are going to have an expansion even though it's 2 dimensions, we have two space dimensions and 1 time dimension. So we have to do the expansion in three dimensions already. When we are in 3 spatial dimensions, we have to do it in 5 dimensions. So it looks ugly, but it's all basic stuff that you learned in the first semester. Yeah. So it's we take this equation, the Lattice Boltzmann equation, up there because it's a little lengthy. I start down here. So it's 0, and then I will, let me see, I will use only one sum, one symbol for the sum. I mean, we have 4 sums, right? three sums. And I will use the indices m, n, and l. They start from 0 and they go to infinity. And I will use t for m, or for the expansion in t, I will use m. For the expansion in x, I will use n. And for the expansion in y, I will use l. And then this goes obviously into m factorial, n factorial, l factorial. So then we are so the distance we are moving will always be delta x half. Yeah, so we're moving delta x half. And we do this in direction n and in direction l, so it will be by the power of n plus l. Okay, is this clear? Yes. So, and then the time will be we also move in half time step, and this will go into the power m. And then we have the derivatives, which I write here in shorthand. So time, the mth time derivative, the nth x derivative, and the lth y derivative. And now comes what we have in here. So we have ix, so we basically will have I by the power of n, j by the power of L. Yeah? Because this is the distance that we are moving here. Yeah? So I times delta x. Yeah? So, and the direction of course gives us the direction of the derivative. This is why ex and ey will no longer appear here, right? Okay? So, and this into Fij. So this is the pre-collision part. Then comes minus the post-collision part. In the post-collision part, you see that we have a minus in front of the distance and in front of the time delay. Yeah. So this means we'll have now here we'll have not I by the power of n, but we have minus I by the power of n, and we'll have minus j by the power of L, and we have minus 1. Yeah. So there's no index in here. There's minus 1 by the power of m. And this goes into Fij after collision. So basically, if you allow me, what we have written here, so let me just remind you that this here is pre-collision and this here is post-collision, yeah, in our nomenclature. Okay. Now this is the Taylor expansion of the Lattice Boltzmann equation. So we said in the title that we will have this expansion in terms of moments, and I mean this is a thing that has been coming up again and again. So you can do the asymptotic expansion in terms of moments, and you can do it in terms of distributions, depending on your taste, and also depending on your purpose. So, for example, when you analyze boundary conditions, it has been shown that because the boundary conditions are often set for single populations, yeah, not the entire node, yeah, then it is often very beneficial to have the asymptotic analysis in terms of populations and not in moments. When you want to derive what we want to do today, derive the partial differential equations for the macroscopic variables, like what is the equation for U and what is the equation for pressure, yeah? Which are moments? Then it makes more sense to do the asymptotic analysis in terms of moments. But this really depends on your purpose, okay? So today we are doing them in moments. So, and here we remind us about our countable moments. Countable moments, MAB. MAB is the sum over I and j. In this case, from -1 to 1, Fij, I by the power of A and j by the power of B. So, obviously, the same can be said for the post-collision, just putting an asterisk here. I, j equal -1, 1, Fij post-collision, I by the power of Aj by the power of B. And this can also be said for our overbar variables that we've already introduced. I from Ij equal to -1 to 1. So the overbar were defined as Ij plus Fij asterisk. So it's the average between pre and post collision. Now I'm running out of space. I by the power of A and j by the power of B. Okay? And whenever you calculate this in practice, this is, if you want to actually implement this, the assumption is, because this will come up, obviously, yeah, the assumption is that 0 by the power of 0 is 1. Yeah, not all programming languages will accept this, so you have to tell them what you think. Okay, in addition to a pre-post collision and the average between pre and post collision, we also have the collision itself. So as the collision itself, I mean the difference between post-collision and pre-collision, and this is what we are going to call omega. Omega AB we define as also a moment. So it's on the same variables, of course, and instead of the sum, it's the difference between after collision and pre-collision, I by the power of j. So basically this replaces pre and post collision. Yeah, we replace pre and post collision by the average and the difference. Yeah. So just the little difference here is that when we have the average, we divide by 2, and if we take the difference, we do not divide by 2. Yeah, that's the only thing to remember here. Okay, I've forgotten something. So I will, because this guy here in the equation 6.3 is so large, I will call all of this together capital T, yeah, just for convenience. Because I will now use this by taking moments of the entire equation. Yeah, so we cannot only take moments of the populations, but we can also take moments of the equation. So what does this mean? We'll take this equation 6.3, which on the left-hand side is 0, and then we do the sum over I and j from -1 to 1. We take this entire thing t, yeah? Take this entire thing t. I should... Okay, I need to be more precise, sorry. With t, I mean the entire thing, including the sum, okay? Yeah, I mean really the entire thing, yeah? So, so the entire equation, yeah, I times a by the power of a, j by the power of b. So I take the entire equation multiply by I and j and integrate, and because we're in discrete form, we just sum up. Yeah? So this is then the moment of the equation. The moment of the equation. Now, how does the moment of the equation look like? So we have this sum over I, j is equal to -1 to 1. And here comes the second sum with m. So this is the sum from the Taylor expansion that starts from 0 and goes to infinity. Here we have 1 over m factorial, n factorial, l factorial. I'm not writing too large now because this will be a large equation. We have delta x divided by 2. And yeah, now we have n plus l, and we have delta t divided by 2 by the power of, what was it, m. Then the t, mth derivative, the x was n and y was l. Okay, now we are still missing the I and the j. They will come up now. We have f, I, j, and here we had already I in the equation 6.3, yeah, I by the power of n. Now we get I by the power of a together with this, so this will give us I by the power of n plus a. Yeah? Everybody clear that where this is coming from? Good. Then we have j by the power of, obviously, what is this? L and b, L plus b. L plus b, and then comes here minus I n, and so once we have minus I by the power of n and we have I by the power of a, so we cannot simply put these two things together, so we'll have to write minus I by the power of n and I by the power of times I by the power of I, right, a. And the same thing with j by the power of, don't get confused with these, L, and j by the power of b, and yes, and minus m by the power of m. So I was just confused why we don't have this minus m for the pre-collision part, but this is of course because it's m by the power of, is 1 by the power of m, will always be 1, right? So this is why it disappears. This is the post-collision, and we are closing the bracket. Okay, now the observation is so the clever thing that you have to understand is that this gives you a hierarchy in moments. Yeah? So we see the sum here is acting on okay, we are, if you put this sum into the derivative here, then you see you're actually getting the moments, but you don't get the moments of the equation, because the moments of the equation were the moments a and b, but you get the moments n plus a and l plus b. Yeah, because so if you integrate over this, yeah, so you get higher moments. So with higher derivatives, you get a higher moment. Yeah, so we can then put this in moment. We put this sum into it, and then we end up with equation 6.4. So there will only be this sum here, m, n, and L is equal to 0 to infinity. You'll have still this guy a lot to write in asymptotic analysis all the time, I'm sorry. N plus L delta T half. By the way, it has, I'm already showing you the much simplified form, yeah? Actually, asymptotic analysis is what computer algebra has been invented for, because they couldn't do it by hand. Yeah, so we can do it by hand because we simplified it a lot. Really, this looked much more messy 20 years ago. We have put a lot of work to get it to the point, simple. Yeah. Okay, now here comes the moment. So, right, by the way, the usage of countable moments has only been coming up in the last 10, 15 years or so. Yeah. So and not everybody agrees with this. So that you can write it as simple as this is because you have countable moments. If you want to have moments like I don't know, with physical interpretation, yeah, then these equations become extremely messy, yeah, as you can imagine. But now we have countable moments. So by the way, we have every second time in this, I mean, if you take n, for example, equal to 1, say, yeah? So then we have minus, minus, yeah? So then this will become a plus. And when we have Fij plus Fij's asterisk, then we end up with an m over bar, right? So in the other case, when this is even, then there will get a difference of them. So we'll have either the overbar version or we have the omega version, right? So so let's write the overbar, m overbar. So as we said, we are counting upwards. We have a plus n. It's now a plus n in the first index, and it is b plus L in the second index. But this will only happen every second time. So, and this will be 1 minus minus 1 by the power of n plus L plus m. Yeah, it depends on, of course, all of them. Yeah, they will alternate. The other way will be omega a plus n b plus L, and they will appear in the opposite case. So it's not 1 minus, it's 1 plus, minus 1 by the power of n plus L plus m. So, and because, as I said, the only difference is that in one case we have already divided by 2, now we have, for the omega, we have to divide by 2. Okay. So this is now the Taylor expansion of the Lattice Boltzmann equation in moment form already. Yeah? So you can do a lot of, some people stop here and analyze just this, which is completely okay, and sometimes it's even beneficial to do this. Yeah? But we go a step further by using asymptotic expansion. And asymptotic expansion is always done in a smallness parameter, and as we've discussed before the lecture, physicists potentially prefer to call this a perturbation. So if you, I'm going to call this thing a smallness parameter. If this makes you any trouble, then think perturbation, okay? So it's a small change somewhere. I mean, smallness, you see, The reason why it's perturbation and smallness parameters because we are looking at different things in this. So perturbation is if you look at a physical reality and see how would your equation behave if you changed something a little. But this is not actually what we mean. What we mean is that we have a discretization. Yeah? And in this discretization, something is small, like the grid spacing or the time step. Yeah? So basically, at the end of the day, this turns out to be kind of the same thing. But it is, I mean, mathematically kind of the same thing. But the point of view we are starting from and what you want to obtain with this is completely different. Yeah? Basically, it has nothing really to do with physics. Okay, now comes a session of a few things that I tell all my students in almost all my lectures. So, because I think they are not, okay, some of you are not been in all my lectures, so it could still be used to new, I mean, maybe it's not new to you, but you haven't heard me saying it. So epsilon is a discretization, specific, scalable. So this is important. This is something that we can choose. Yeah, we can choose the resolution. If we cannot choose, then there's no smallness parameter. So what is typically typically it would be the grid spacing, yeah, size of your finite element, something, the grid spacing, or the time step. See, you already see the problem because we have grid spacing and time step. So if you learn Gaia, yeah, if you come to my lectures on numerics, I always start with the following. Numerical approximation. I mean, first we have to, what is a numerical approximation? Very, very basic. A numerical approximation is any function f of x and epsilon, which gives you f of x, and this is the true thing, the true function that you are looking for. Yeah? So the idea is you cannot evaluate this function, otherwise the true function, otherwise you wouldn't do any numerics. So you have an approximation phi of any sort that is the true function plus a sum. So with this I mean an expandable error. So this is a power series in the smallness parameter. So there's a series of error terms. So this is my definition of a numerical approximation. So the method that you are using is said to be consistent if the following holds, that the limit of epsilon going to 0, or in the limit of epsilon going to 0, this replacement function fx and epsilon goes to fx. So saying it converges for the smallness parameter going to 0, yeah, then it's consistent. So basically saying the numerical approximation phi, x, and epsilon is the truth plus a hierarchy. So it's important that we can build a hierarchy of error terms. And these error terms are separated because we have this power series of the error terms by powers of epsilon. So I don't know whether you have heard this, but this is the basic foundation on which this is the assumption, so to speak, that this holds for numerical methods in general, or at least for those which we intend to analyze. Yeah, it may be a little bit the one where this becomes difficult is Monte Carlo integration. Yeah, then it's not so clear how to define these things there. But say we are in a deterministic setting. Okay, so if our approximation is always the truth plus a series of error, then it should be possible to write everything that comes out of our analysis. So this would be, for example, the moments in a series just like this. So we go from n from 0 to infinity, and now we take the power series epsilon of n and multiply this with parameters of this moment. Yeah, so infinite sum, of course. The same thing for this collision thing. So we start from n equal to 0 and going to infinity. And here we have the power series in epsilon over AB and the order n. Now, there must be something very important to remember, this MAB. So the reason why your asymptotic analysis does not work is maybe because you missed this small little point, okay? So these coefficients in the series expansion, yeah, they are not functions of epsilon. So they must be strictly independent of epsilon. Meaning that all the information on epsilon is put actually in the series. Yeah? So you build the series, and then the coefficients themselves are independent. Only the series depends. Is this in any way confusing?
Yes. So what you just said is that we cannot write the countable moments of the collision in terms of this small.
No. We write. Okay. So this is what our what the numerical method delivers. Mm-hmm. Yeah. So we have no idea actually what MAB by the power of whatever. No, there's no power. Order. This with brackets we mean order. Yeah. So we have no idea right now what this is. I mean, of course, we do the analysis to find out. The thing is, we know that MAB depends, the result of your simulation depends on your smallness parameter, on your grid spacing, obviously. Yeah? So, and we put all this dependence in the series expansion, such that the coefficients themselves do not depend on epsilon. Because you could always write anything, yeah. So because this is the only thing that makes it unique. If they still depended on epsilon, yeah, so then the series would not be unique.
Okay.
Yeah, because you could always put some part of this inside here.
Mm-hmm.
Yeah. So, but anyway, even though this could be clear, it's a mistake that's often done. Yeah. And that there's still a dependency not taken care of. Okay, let's look on the things that we actually want to solve for. So there's a density and velocity of the, okay, we call this lattice BGK. This is why it's LBGK. So we will have density rho. This is the outcome here, and we say this density rho we must be able to expand this as a rho 0 plus an epsilon rho of the order 1 plus an epsilon square rho of the order 2 plus dun 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 dun. So this is the asymptotic expansion of rho. Yeah? Then we have a velocity u, which we can asymptotically expand in 0 order plus epsilon first order plus epsilon square u second order, yeah, and so on for forever. Okay, so this is for a general epsilon, but we have not determined what epsilon is. And of course we have a problem because we are doing fluid dynamics, and in fluid dynamics, problems is our second name. Yeah, so problem, LBM has two numerically small parameters because there is a grid spacing and we have a time step. Delta x and delta t. Okay, so one possibility that you could think of is accepting that you have two and try to do a two-dimensional analysis. People also have done this. But this doesn't give a clear answer, actually. I mean, you can try, yeah, believe me, you run into some trouble, but if you like, try. So what we actually have to do in order to do an expansion like this up here of our moments, if we want to expand only one smallness parameter, we have to somehow link these two parameters together, that we end up with only one. And because we have two, we have different choices for epsilon, and even you may think that it should be clear how to do this because we have fluid dynamics and problems is our second name. You'll see that it is not obvious how to do it. There are two, okay, say there are two obvious, now I've just said there's not obvious, yeah. There are two things that come to mind, let's say, two obvious choices, and they, both of them have their limits. And they will be called acoustic and diffusive scaling. So, what is acoustic scaling? Acoustic scaling So this is maybe what you could think of the most obvious, first coming to mind. You say epsilon, delta x is proportional to epsilon, and you say that delta t is also proportional to epsilon. So you scale both with the same way. This obviously leads to this thing, which will turn out to be a problem, that delta x divided by delta t, which is the lattice speed. This thing is constant. So this also means that the speed of sound, which we have identified to in Lattice Boltzmann CS to be, yeah, you remember 1 over square root 3 delta x by delta t. This is also constant. Meaning that the speed of sound is invariant under scaling. And this, of course, is the reason why this is called acoustic scaling. So, what does this lead us to? We have not only two of small parameters, but we also have two dimensionless groups in the Navier-Stokes equation, dimensionless numbers, which are the two dimensionless numbers in the Navier-Stokes equation? Not Boltzmann, Navier-Stokes? Reynolds and Mach. So yeah, we have the Mach number. So it will be, so because I'm using things without star as dimensionless numbers, I will now put dimension carrying variables with a star, right? Because, so this divided by CS, say this is a physical velocity scale. The Mach number, the Reynolds number, is, okay, different ways of writing it. We write it with the kinematic viscosity. So L is a physical length scale, and nu is, okay, what is nu? Nu is the speed of sound, so in Lattice Boltzmann, the speed of sound, 1 over omega minus 1/2 delta t. So this is our viscosity. If we plug this viscosity into our Reynolds number, we get Reynolds number is equal to U star L star divided by CS square 1 over omega minus 1/2, and here comes delta t. Now what we can do, we can identify that here is U star and here is CS, so we'll find that there is a Mach number included in this, and we can write Mach number times L star divided by CS 1 over omega minus 1/2 delta t. So in this thing, everything is scale independent up to delta t. Yeah? CS, we have said that this is, so L is the outside, L star is the physical outside length, yeah, has nothing to do with the grid spacing. CS is constant, Mach of course is a physical parameter, and Reynolds number is also a physical parameter. Yeah? So they should be scale independent. The only thing that gives us a scale is delta t, and this is still in it. Yeah, I mean, this is, okay, so this is one of the mistakes that you can do in this analysis, that you forget that the Reynolds number must be independent of grid spacing. So this is a big problem with the Chapman-Enskog expansion, because they assume that the Reynolds number, the Chapman-Enskog expansion, which we are not talking about today, assumes that the Reynolds number is scaled. Yeah, because it has the Chapman-Enskog expansion is not there for analyzing numerical methods. It's only some people misuse it for analyzing numerical methods. It is there for analyzing the relationship between kinetic theory and continuum theory, right? Yeah. So it's a physical thing, and there is no discretization in physics. The only discretization that you're looking for is that down there's no continuum, but there are molecules. Yeah, this is something like a discretization. Okay. So, as I just said, Mach and CS also independent of spacing. So the only thing that we have still here is delta t, saying that Reynolds number, okay, right, so I rewrite this equation to Reynolds number, put the CS up, L star Mach number, and end up with the numerical stuff on this side, 1 over omega minus 1/2 delta t. So now everything on the left is constant. Yeah? So then obviously the right must also be constant, and this means for 1 over omega that this is L star m divided by Reynolds times CS. So this is the constant part divided by 1 over delta t plus 1/2. So here's the scale dependent part in it. Okay, so very important, I cannot overstate this. In acoustic scaling, so epsilon is proportional to delta t, yeah, and this is proportional to delta x. Omega is a function of the resolution. And this you have to take into consideration when you do an expansion. Yeah, you have to expand omega. And if there somewhere is an omega included, you have to expand this somewhere included. Yeah? Because if you don't do this, you're messing up. And I mean, I'm overstating this because I've spent now near to 20 years, I guess, to point out to very senior scientists in the field. They always agree on the spot, and next year I have to explain it again. So this is why I'm now already getting a little bit furious about this. So ignoring the dependency of omega on delta T in acoustic scaling. Is a persistent error in the literature. You will see this again and again, and then don't tell me, but he has wrote this and this is a paper, and you're, no. This is wrong. Please remember, literature is an evolution, yeah? So there's a lot of stuff in literature, what I wrote including, yeah? Is a lot of mistakes. Also, this lecture has a lot of mistakes. Yeah, always remember. So another thing, of course, the lattice speed. The lattice speed is also not small. Is not, as we say, asymptotically small, so that it gets smaller when you refine. Because delta x by delta t, which is the lattice speed, this thing here is constant. This is a bigger problem that you may think. Yeah, because we have a discretized velocity range. And if you discretize something and you have no smallness parameter in that discretization, you can never have convergence. Yeah? So you discretize velocity, but velocity is not small, yeah? So it will never converge. I mean, asking for convergence in acoustic scaling is just, you're asking something impossible.
I have a question.
Yes.
Is that why when in the Lattice Boltzmann, when we have higher velocities, or it has to be bounded, the velocity? That's why
the velocity has to be bounded. So what people do, I mean, there's this, good thing is that nobody important now, you're all important, sorry. No. I mean, somebody who's doing this for a long time, yeah, you obviously come here to learn Lattice Boltzmann. Though the guys who already know Lattice Boltzmann, of course, they don't listen to my lecture, yeah, this is what I meant with saying, sorry, yeah. So they usually like acoustic scaling, but what they have to do, this is what I just wanted to write, they have to do additional assumptions. You can use acoustic scaling and then assume on top of this that velocity is small. Okay, they say we do acoustic scaling and we just assume that velocity is already so small, yeah, that we don't care about these errors. Yeah? It's just that from a mathematically point of view of convergence, the error in velocity is then independent of the resolution. You make your grid finer, this error is not going away. Now if you say, we've already taken care that the velocity is small enough that we don't care about errors in velocity anymore, yeah, then you are fine, yeah. Okay, so but we don't get okay now, but it doesn't work mathematically. So now let's look at what's something that actually does work, and this is the diffusive scaling. Diffusive scaling. So, and the idea here is now we want to keep the omega constant. Because omega is defining diffusion, yeah, this is why the thing that is kept constant during scaling is giving the name. So it's the diffusive scaling. And diffusion is, of course, a viscosity. Lattice scale independent. So what do we have to do? We have the Reynolds number, U star L star divided by CS square 1 over omega minus 1/2 delta T. And this thing is, of course, supposed to be constant. CS square we define as theta. Now you could say that this theta is 1 over 3, but okay, forget this for the moment. We leave it open. Yeah. So theta, by the definition of this is the dimensionless temperature. Okay, temperature is related to the intensive quantity of the energy, right? So this would be speed square. Yeah, speed is intensive. Yeah, speed square is, so to speak, the intensive energy, and the intensive energy is the temperature. So then tau theta is the temperature. So we can plug this into the Reynolds number, U star L star. Now we say that here is the theta, delta x square by delta t, and here we have 1 over omega minus 1/2, which we want to keep constant, and multiply this by delta t. Now if you look at, okay, when we want omega equal to const, then this is the case when delta x square is proportional to delta t. Yeah? Because here's square missing, delta x by delta t. So we can cancel out one delta t, yeah, and then this will turn out like this. So we have CS. CS is, of course, now the square root of the temperature, delta x by delta t. If we plug in our scaling, theta, epsilon by epsilon square, which is, of course, this root 1 over epsilon, which means that when epsilon, remember epsilon is going to be small, we want to have convergence. If epsilon is going to 0, this means that the speed of sound goes to infinity in this limit. Yeah? And because the speed of sound is going to infinity, so this is the reference, yeah? The speed of sound is also proportional in lattice Boltzmann to the lattice speed. Yeah? So the lattice speed goes to infinity such that the speed we are so when the lattice speed is going to infinity, then the speed we are simulating with is going to 0, is small compared to the reference. Yeah? And therefore we have convergence in speed. Yeah? So what do I have? So the simulated velocity is asymptotically small compared to the speed of sound and the lattice speed. Okay, obviously this has also the implication that the Mach number is now not scale invariant, yeah? Actually, we go to 0 Mach number in convergence, obviously. When speed of sound goes to infinity, and the Mach number. So if you don't like this because you want to do acoustics, then, well, so bad for you.
I have a question.
Yeah.
In the speed of sound, we have the speed of sound is the square root of delta x divided by delta t. And delta x is proportional to...
The speed of sound is the square root of...
Delta x, yeah, it's the last thing you have up, yes.
Yeah. Of theta.
Yes. And delta x is proportional to epsilon. And delta t is also proportional to epsilon, right?
No. Delta x square is proportional to...
Okay.
This here is acoustic, this here is diffusive scaling. This is the important thing.
Yeah, thank you.
Yeah. Okay. Speed. So our physical speed, u star, is u, so the dimensionless thing, times delta x times divided by delta t. Dimensionless. So our u in the simulation is u0, which we treat as a constant, and because this in diffusive scaling is going to be smaller, so this, because this will be epsilon, right? So this means that we have nothing in the zero part, but we have the solution in the first part. So this is something that does not happen in other numerical methods usually. It means that even our solution scales. Yeah? So we cannot use the actual velocity of, so you cannot do Lattice Boltzmann by putting in the velocity in meters per second. That doesn't work. If you scale down, even the velocity is getting smaller. And later when you analyze your data, you have to upscale it. Yeah? Because in most numerical methods would use the zero order, yeah, the one that is constant, as their solution. But here we use the first order. Okay, plus now second order, epsilon square plus and so on and so on. And these things here are the error. So let's do an asymptotic. What am I writing? Asymptotic expansion of LBGK in diffusive scaling starting from our equation 6.4. Okay, writing down the equation 6.4 again. n L from 0 to infinity, 1 over m factorial n factorial L factorial, get epsilon, no, sorry, there's not yet an epsilon in it, delta t half divided by the power of n delta x half, wait, this is wrong, this must be m. This is n plus L dt m dx n dy L, and now we have the moments m a plus n b plus L comes here 1 minus 1 power of n plus L plus m, and minus omega a plus n b plus L divided by 2 together with 1 plus minus 1 n plus L plus m. Okay, so this is the equation, and 6.4, and now we write the equation 6.5 by introducing the asymptotic expansion of the moments in here. So this will again be 0 equal to m n L equal to 0 to infinity, 1 over m factorial n factorial L factorial. Now instead of what we have here, we'll end up with epsilon, and now remember that epsilon is, that delta t is epsilon square. Yeah? So then we'll have epsilon by 2m, yeah, plus n plus L. And now we have something in addition, namely the q, and we start q, we sum up q from 0, yeah, with every moment that, with every order that we sum up, we get 1 q more. Then also we have to, because we always divide by 2, we have to take this 2 by the power of m plus n plus L. So this goes into our derivatives here. And now comes this magic, a plus n, b plus L. So where's the q? The q is the orders, yeah, in which we expand. We're expanding the orders. Yeah? So it's by the order q, 1 minus minus 1 by the power of n plus L plus m, minus omega a plus n, b plus L, and we are also expanding omega in terms of q, this half, this is 1 plus minus 1 n plus L plus m. So now we have this epsilon in the equation, and we want to get rid of this epsilon by doing equating coefficients. So the idea behind this, very, very powerful idea, is basically, the idea is putting a series into a sequence. Yeah, this is what you do by equating coefficients. We assume that epsilon is arbitrary, epsilon, but larger than 0. And this means that the equation 6.5, which is equal to 0, will be 0 for all epsilon not equal to 0 only if each term of the epsilon order of not q, because we have written this already, EP is 0. I mean, the idea, very briefly, a plus b epsilon plus c epsilon square. We have something like this, yeah? So this should be now true for all epsilon larger than 0. Then this will only be true when A is equal to 0, B, when they are individually equal to 0, right? So this is what we call equating coefficients. So, and this means we can look at all the sums that we want to take in we can make from this series a sequence, which, okay, the sequence still is a series inside, yeah, but it's a sequence in epsilon. Right, so this then looks like this. We got from M, N, and L equal to 0, and Q, but Q now must be P. P is the one that we give in, minus 2M minus N minus L. Yeah, so this means we are saying that we take all the terms where 2m plus n plus l plus q are the same in this equation, yeah, and just look at these. And they go to infinity, so we have 1 over m factorial, n factorial, l factorial. We still have 1 over power m2 plus, by the power of n plus l. So this all in 3 dimensions gets more annoying than this. The derivatives here, and then we have ma plus n. So this is by the power, not by the power, by the order q. This is b plus l, 1 minus 1 n plus l plus m, minus omega a plus n plus b plus l. This half, this is to the order q, half, and this times 1 plus minus 1 n plus l plus m. So some people say at this stage, I've lost you. You lost me. The good thing is we are done. Now this is a very powerful equation, because this equation, if we plug in a P, an A and a B, we directly get the differential equation that we are solving. Yeah. So let's and sometimes we can even do this without plugging explicit Q's in it. So okay, one thing that is important to remember is that these guys here are expanded in positive orders. Yeah, this means they are 0 whenever q is smaller than 0. Yeah, so they will disappear in the negative. Yeah. So now what we do is we plug into this equation up here. We will plug in p equal to 0, which means we are looking at epsilon to the power of 0, and we leave A and B open. Then the only thing from everything that is in here that remains, yeah, is minus omega AB to the order of 0, and all of this is equal to 0, which shows you that to the order of 0, the collision operator is always 0. Okay, not a lot of information, but important anyway. P equal to 1, meaning we look for the terms in epsilon to the power of 1. what comes out of this equation is dx ma plus 1 plus b by the power of 0. By the way, because this is by the power 0, this thing here is a constant, as it does not change with space. So, which means you dy a b plus 1 to the, must be an overbar. This here is also const. So because it's const and you take the derivative of it, it will disappear. We have here omega equal to omega ab to the order 1, and this is equal to 0. So because these two guys are constant and we take the derivative, they will also disappear. And you see that the first order of omega, is always, no matter what a and b is always 0. Okay? Do we get more interesting information? P equal to 2, meaning epsilon to the power of 2. So this is the first time when the time derivative does not disappear. Yeah? So we get dt MAB by the order of 0. So anyway, it means it still disappears because this again is constant, so it does not, if you take a derivative of it, it will disappear. Plus dy MA. So the space derivatives, they give you always an order less, b plus 1, so this is now first order, the x ma plus, what am I doing? Oh, yeah, I mean it's correct, I just don't know why I put y first. B 1 minus omega ab second order equal to 0. Now, not everything out of this will disappear, obviously. The only thing that will disappear will obviously be this. Next page. Going to P equal to 3, and so epsilon by the power of 3, and fortunately this will be the last that we actually need, because now we get a proper time derivative, MAB omega over bar 1 plus dx MA plus 1 B, and here will be 2, plus dy MA and b plus 1 over bar, here will be 2, minus omega ab, and here will be 3, and this is still equal to 0. Okay, so from these we can derive everything that we need. Let's look at epsilon square again, but now it's putting a to 0 and b to 0. You get to dt m00 over bar order 0. As I said, this is constant, so it will disappear. M10 to the first order plus dy m01 to first order minus omega 00 to second order. Now we are talking about zero moment. Zero moment is conserved. Because it's conserved, it means that it does not change. So omega is 0. Also, M00 over bar, this is rho to the 0 order. This is constant, so it will disappear. M10 to the first order is rho 0 ux first order plus rho first order times ux0. ux0, constant velocity, we assume constant velocity is 0, yeah?
The order is, the first u is order 1, right?
This is order 1, this is our solution, yeah? So, and then we also have m01 first order, this is rho 0 uy first order plus rho first order uy 0 order. So again, this here disappears. So, and if you plug these things into the equation above, what you end up with is dx rho 0 ux first order plus dy rho 0, which all is constant, so you can plug it in front, is equal to 0, and this obviously gives you rho 0 order divergence of u first order is equal to 0. Yeah, so this is your first equivalent PDE derived from asymptotic analysis. Sorry for speeding up, but I'm really in trouble because I have to catch a train. So let's see epsilon by the order of 3, a equal to 1 and b equal to 0, and this is what we're going to call equation 6.6. dt m10, so yeah, we plug in 1, so we end up with the moment here 1, 0, plus dx m2, 0 to second order plus dy m11 to second order minus omega 10 third order is equal to 0. Now, in order to get, so these moments are not conserved. So in order to understand what they are, we have to take the, okay, so of course, first of all, they are, this is the definition of the overbar, and then the BGK. The BGK equation basically gives us that the post-collision is AB plus omega MAB equilibrium minus MAB. Yeah, and we call this here equation 6.7. Since omega AB is MAB asterisk, so after collision minus MAB, we can rewrite this MAB as being MAB over bar, the guys that we actually want as our solutions, minus the collision operator half and MAB after collision is MAB plus half a collision, I mean, which makes hopefully sense. Overbar. So then from 6.7, which is the collision operator, we can write that MAB over bar plus omega AB half is MAB over bar minus omega AB half plus omega MAB equilibrium minus MAB plus omega AB half, and this leads us to omega AB being small omega MAB minus MAB plus omega AB half, which again can be rewritten as MAB over bar, which we actually were looking for, is MAB equilibrium minus 1 over omega minus 1/2 omega AB, and this now we plug into equation 6.6, which gives us dt rho 0 ux1 plus dx m20 equilibrium minus 1 over omega minus 1/2 omega 20 second order dt dy m11 equilibrium first order minus 1 over omega minus 1/2 omega 11 second order. And still we have this omega 10 to third order, and all of this is equal to 0. Now we have to plug in the equilibria for this. So we have M20 equilibrium to second order is theta, so the speed of sound squared, times rho second order plus ux. So ux, because ux is first order and we take it square, yeah, it is the square of first order is second order, right? Times rho 0 order. We also have M11 equilibrium to second order is equal to ux first order times uy first order. Yeah, so and this together with rho 0 order. So that together they get to the second order. 6.8, equation 6.8 is then dt rho 0 ux first order plus dx theta rho second order plus ux first and plus dy, so the derivative in y direction, x first order uy first order rho 0 minus, I've taken out this viscose part, 1 over omega minus 1/2 dx rho 0 to 0 second order plus dy rho first 1 to second order minus rho collision operator 1 0 to third order. All of this is equal to 0. And this leaves us with the solution for, we still need epsilon for the second order moments or the second order collision operator, epsilon square, so second order A equal to 2 and B equal to 0. Then we get dt M20 of 0 order, because this is constant, it disappears right away, plus dx M30 first order plus dy M21 first order minus omega 20 to second order is 0. Now what we have to do is we have to look into, so we get omega to second order, we can, is dx M30 to first order plus dy M21 to first order, and since they are only to first order and the first order of the collision operator is also always disappearing, we know that this here is equal to their equilibrium. So we only need the equilibrium of the third order moments, which is of course something that we've discussed a lot before. AB first order is equal to 0. So, and then we go to M30 equilibrium is actually this alien. So first order is rho 0 ux, yeah, that's the alien. Then we have M12 equilibrium, first order is theta times ux, first order. M21 equilibrium, first order is theta uy, first order, and we plug all of this into 6.8. Oh my God, I have to be on the station in 10 minutes. dt rho 0 ux, first order, plus dx theta rho second order plus ux first order squared rho 0 plus dy ux first order uy first order rho 0 minus 1 over omega minus 1/2. Here comes dxx, so second derivatives now. This comes out of the first order, this comes out of the third order moments, dy y. So there's a theta ux first order rho 0 plus dxy 2uy first order theta rho 0 minus omega to 1/3 order. And now we're calling the entire thing in here, we call this an A. So A is equal to rho 0 theta dxx ux first order plus dy y ux first order dx ux first order. Now we can take here 1 minus theta. Oh my God. Theta rho 0 plus dy 2 uy first order theta rho 0 order. Okay, it was a bad idea to book this train. Equal to B. So B is a thing that we don't want to have. So we put this to 0, and we know that this here to first order is 0, and we get this when 1 minus theta is equal to 2 theta, which implies that theta needs to be 1/3, which is of course what you already had. And then we finally get dt rho 0 order ux first order plus dx, so ux first order square rho to the order of the order 0 dy ux first order uy first order rho 0. So this is the right-hand side of the left-hand side of the Navier-Stokes equation, and on the right-hand side we have dx theta rho second order, which is the pressure, plus theta rho 0 1 over omega minus 1/2, which is the viscosity, into dx x ux first order plus dy y ux also first order, and we have in addition plus omega 1 0 to third order, which is a body force, and this is the Navier-Stokes equation, and I am off. Thank you very much for coming and listening. Yeah.